The last thing we want to look at in this lab is how to calculate RMS values for currents and voltages. We'll look at voltages, but it works for currents exactly the same way. Okay, here we have a typical alternating current type voltage, which is behaving like a sine wave. We can follow the voltage, it's going down, it's going up, repeating over and over in a sinusoidal fashion. Now, one of the things that is interesting is to note that when you have a sine wave, its average is going to be zero. It's going to be zero because it's above the zero exactly the same amount of time as it's below the zero. And so when you average these values together, they're like a mirror image, and they end up, over time, canceling out and averaging to zero. So the question arises, how could you possibly use an alternating current system to drive anything if the average of the voltage being supplied is equal to zero? And it turns out that while that is true, the voltage isn't the most important thing for determining that. In order to understand that, let's think about what we're actually seeing in this trace. So of course, this oscilloscope is measuring the voltage as a function of time. So in other words, if I pick a particular time, say right there, I can go up and I can read off what the voltage is at that instant in time. So a question arises, what would you measure if you put it in just a regular old-fashioned voltmeter like we've used before? So here's the typical digital voltmeter that we have used in lab previously. And you can see there are settings for measuring direct current voltages, and we know that's when the voltage is constant. There's also settings for measuring alternating current voltages, and that's when you have a varying voltage like the one that we've seen previously. So what would you measure if you plug that voltage into the digital voltmeter? Well, it turns out you get a value known as the root mean square value of the voltage. Okay, here you have a picture of a typical sine wave, and there are a few different values that are labeled, and we just want to take a look at those real quick. Obviously, we have the amplitude of the sine wave here, and then it's going to be the same value down below, only negative. And we know that from the center up is the peak voltage, and from the bottom to the top would be the peak-to-peak voltage. These are all things that we've seen before. We know the average voltage is going to be zero. That's not indicated here, but we do know that. And then there's this third one here, or fourth one, I guess, the root mean square voltage, which is equal to 0.707 times the amplitude. It turns out that value is very, very special, and it's related to the amount of power that this voltage is going to be able to deliver to a circuit. In order to understand that, let's think about what the function would look like for this kind of a voltage. Typically, you're going to have the voltage as a function of time, which is going to be given by something like V equal to some amplitude, we could call that V naught, times a sine of 2 pi f t. And of course, the frequency is the f value and the time is the t value, and the 2 pi gives you a measurement in radians. So frequency is 1 over seconds type units, time is seconds type units, so the argument of the sine wave is dimensionless as we expect, and this is the functional sort of behavior that we would expect for a sine wave. I'm sure you've all seen that before in your trigonometry classes, so hopefully that's not a shock. So let's look at applying that voltage into our formula for power. Now we know that power is given by the voltage times the current. So P is equal to IV, that's the current times the voltage here. But if Ohm's law applies, we know that V is equal to IR, or I is equal to V over R. And so if I plug in this guy for I get V squared over R is the power, and then I can plug this value of V in to get the full expression. So the power is simply going to be P is equal to V squared over R. That's one of our formulas for calculating the power. And we can use that and ask the question, how do you calculate the average power? Now here I've got the power and I've put a little bar atop it to indicate that we're taking an average. And so that's just going to be v squared over r. And I can plug in that expression we have for v naught sine of 2 pi ft, everything squared, and then I take the average. And so when I do that, I can clean this up a little bit, and I get that the average power is going to be v naught squared over r. Why was I able to pull those out? Because v naught is simply the maximum value. That's the amplitude of the sine wave. It's just going to be a constant. R is the resistance in the circuit. That's going to be a constant. So I can pull these guys out because the average of any constants is just going to be that constant. And I'm left with the average of the sine function. Specifically, the average of sine squared. And that squared is what's really important, because when you average the sine function, it goes to 0. But when you average the sine squared function, which is what we're using to calculate the power delivered to the circuit, the square makes it not 0. Because we know that all the values that you get from something squared have to be positive. If we look at a plot of sine squared, we can see that it goes from 0 to 1, and it oscillates back and forth, but it's never negative, because that's what happens when you take the square of something. So normally the sine wave would be going up and down, but it flips up when you square the negative values down here, and you're left with a curve that looks like that, going from 0 to 1. Now it turns out that the average of sine squared is right smack in the middle at 1/2. Okay, so let's look at the sine squared. You might remember from trig that there is an identity that the sine squared of something is equal to 1 minus the cosine of 2x all divided by 2. And so if I want to take the average of sine squared, that's the same as taking the average of that guy. But that's going to be equal to the average of 1/2 minus the average of cosine of 2x all divided by 2. And we know that the average of a cosine averages to 0. And so what we end up with is that the average of sine squared simply leaves us with 1/2. And that gives us that sine squared average is equal to 1/2. So we can apply that to the formula we had on the previous slide, which was P average is V naught squared over R times the average of this sine function. Well, we now know that the average of this sine function is simply going to be 1/2. And so that tells us that the average power is 1/2 V naught squared over R. Again, R is the resistance in the circuit, and V naught is the amplitude, the peak amplitude of our voltage. Now what's interesting is that this formula looks very similar to the normal power formula, which would be V squared over R. And so the question is there some value of V that would be equivalent to this expression? And of course there is. We can simply set these together, set these equal together, and solve for this voltage here. So if we do that, we have 1/2 V naught squared over R is equal to, and I'm calling it the root mean square voltage squared divided by R. And you'll see why that is in a moment, why we have that name. But canceling out the R's, that leaves us with the root mean square voltage is equal to V squared over 2. And the RMS voltage then is simply determined by taking the square root of that, which leaves us with V naught over root 2, or that the root mean square voltage is 0.707 V naught. And that's that number that we saw previously. That's where that comes from. So what does this mean? Well, if we had a DC circuit, one where the voltage was not alternating back and forth, then we know that the formula would be V squared over R. But because we have the voltage, which is varying like a sine wave, the power formula is V naught squared over R. The reason that we like this VRMS value, the root mean square value, that's because it behaves like the voltage in a DC circuit. So all the formulas that you know from analyzing DC circuits, they can be applied using the root mean square values in alternating current circuits. And of course, calculating these values is pretty plug and chug. The root mean square is just 0.707 times the peak voltage. In your quiz, there are a couple of examples where you have to calculate those, and frankly, I'm hoping that those are free points for everybody because it really is just that easy, plug and chug.